Hello friends, today we are going to see the trick by which we can solve any RLC based transient sum very easily, very fastly. Okay, so before we jump to the trick, let us see the type of the question that we get in our GATE exam. So the first type is where we have to find out the capacitor current or capacitor voltage, inductor current or inductor voltage, or any branch current or any load voltage. Okay, and the second type is where we have to find out I0 plus V0 plus. This can be of your capacitor, inductor or any branch. Okay, the third type is where you will be given what is the type of your system, and accordingly you have to find out the condition of your RLC from the option. Okay, so let's see all this type of the question from sums one by one. Okay, so let's start with the first sum, where in this sum it is given that for t greater than equals to 0 the voltage VCT is. Okay, so the question is asking about the voltage across this capacitor for t greater than equals to 0. Okay, and in the same question we have second question that for t greater than 0 we have to find out the voltage across resistor. Okay, so basically we have two questions in this question, that is we have to find out the voltage across capacitor and the voltage across resistor. Okay, so let's see the solution one by one. Okay, so let's start with the voltage VCT. Okay, so let me tell you, for all this type of question, basically for this first type we are going to use Laplace transform. Okay, for this two type we will see what we have to use and not to use. Okay, so here we are going to use the Laplace transform. Okay, basically we are going to transform this circuit into Laplace domain. Okay, so to transform this inductor we will require SL, and in series with the negative voltage having the magnitude of L into IL0 minus. Okay, so it means that we require IL0 minus. Okay, and if we transform this capacitor into transform domain, it means we will be having 1 upon CS in series with the positive voltage with magnitude of Vc0 minus by S. Okay, so in both of these you see that we require IL0 minus and Vc0 minus. Okay, so that's why first we will calculate IL0 minus and VL0 minus. Okay, so for that we will use t equals to 0 minus wala period. Okay, so here you can see we have a voltage source of del t. Okay, and as we all know that del t is present only on t equals to 0, not before t equals to 0. Okay, so here in this period we are before t equals to 0. Okay, so it means this voltage will not be present for this period. Okay, so if you draw this circuit you won't be having any voltage source or current source present, so it means whatever the voltage or current will be there, it will be 0. Okay, so Vc0 minus is 0 volt, IL0 minus is 0 ampere. Okay, now let's see for t greater than 0. Okay, let me tell you, we do Laplace transform only for t greater than equals to 0. T equal to 0 minus is our requirement. Okay, as our t greater than 0 requires some parameter from t equal to 0 minus. Okay, so in t greater than 0 we will transform all elements into Laplace domain. Okay, so this del t will be transformed to Laplace domain, so it will be converted to 1. Okay, del t Laplace transform is 1, right? And this L will be transformed to SL in series with the negative voltage source of L into IL0 minus. Since IL0 minus is 0 ampere, so that voltage will be 0 volt, so it will be replaced by this short circuit, and this is our inductor which is S into L. L is 1 Henry, so it will be just S, and this capacitor will be transformed into 1 by SC. C is 1 farad, so it will be replaced by 1 by S, and in series with the positive voltage source of magnitude of Vc0 minus by S. Since Vc0 minus is 0 volt, so we will replace by 1 by S. Okay, so this is our transform circuit, and now from this we have to calculate our Vc of S. Okay, so here if you observe this circuit, you can clearly see we can use our voltage divider, or we can find out the current flowing in this circuit, and then just by multiplying 1 by SC we can get our VCS. Okay, here we are going to use voltage divider as this is more simpler. Okay, so VCS will be 1 by S upon total resistor, so it will be S plus 1 plus 1 by S. Okay, into input voltage source which is 1. Okay, so it is 1 by S upon S plus 1 plus 1 by S multiplied by 1. Okay, so if we simplify it, it will be 1 upon S, and if we multiply this S to all this term, we will get S square plus S plus 1 upon S. So this S got cancelled, and we will be remaining with 1 upon S square plus S plus 1. Okay, now we have to take the inverse Laplace transform of this. Okay, so to take the inverse Laplace transform of this, first we are going to make this complete square. Okay, so S square plus S plus something such that this will be converted to complete square. Okay, so here we are going to compare these two terms with our a square plus 2ab plus b square. Okay, so from a square you can see that a is your S And if you compare your 2ab equals to s, you will get that your b equals to 1 by 2. Okay, so in that way you are adjusting your denominator. Okay, so here you will be having s square plus 2 into a into b. A is your s, b is your 1 by 2, plus b square, which is nothing but 1 by 2 ka square is 1 by 4. Then you will be left with 3 by 4. As you can clearly see, in denominator you are having 1, and just to adjust to perfect square you have written 1 by 4. So whatever the left part is, that your 3 by 4. Okay, now we can make this term as s plus 1 by 2 ka whole square plus this left portion, which is 3 by 4. Okay, as you all know, the sin 80 Laplace transform is a upon s square plus a square. So we have to make this term also into a square. Okay, so what we are doing is we are taking root and then taking it to square. Okay, so that doesn't change the value, but it will be in the square form. That's what we need. Okay, so it will be under root of 3 by 4, basically under root of 3 by 2 ka whole square. Okay, so this is what every time. Okay, now if you take the inverse Laplace, okay, so first we have to remove the effect of exponential, as we have already discussed. Okay, so we will be having e raised to minus 1 by 2. Okay, then we have to take the Laplace inverse of the remaining part, which is 1 upon s square plus under root of 3 by 2 ka whole square. Okay, now if you see carefully, we have 1 upon s square plus a square. So it means the inverse Laplace will be 1 upon a, which is nothing but a is root 3 by 2. Okay, so 1 upon root 3 by 2 into sin 80. Okay, so sin root 3 by 2 t. Okay, now if you just rearrange it, it will be 2 by root 3 e raised to minus 1 by 2 sin root 3 by 2 t. Okay, so this is your answer for VCT. Okay, and if you compare this by your option, you will get that your this D option is the correct one. Okay, now let's find out the answer for this second question. Okay, so in second question we have to find out the voltage across this resistor. Okay, so the voltage across this resistor will be the current flowing through this circuit multiplied by this R value. Okay, and if you observe this carefully, you will see that your resistor current, your capacitor current, and your inductor current all are same. Okay, since we have already calculated our VCT. Okay, so from this we can get our capacitor current. Okay, which will be equals to our IRT, basically the resistor current. Okay, and then we are going to simply multiply with the value of R, such that we will get our VRT. Okay, so this is what I have written here. VRT is R into IRT. IRT is simply equals to ICT equals to I of t. Okay, so first we have to get our ICT. ICT we are going to get by this VCT. Okay, so ICT is nothing but C d by dt VT. Okay, VT is this we have calculated just now. Okay, so it is d by dt 2 by root 3 e raised to minus t by 2 multiplied by sine root 3 by 2 t. Okay, and from the Liet rule we can see that this is trigonometry function and this is exponential function. Okay, so we have to take t first, then e. Okay, so this trigonometric part will be our u and this will be our v. Okay, so we have taken this constant part outside, so this is 2 by root 3, then u derivative of v. Okay, so this is our u, derivative of v will be e raised to minus t by 2 multiplied by minus 1 by 2. Okay, so this is what I have written, then plus v derivative of u. Okay, so this is your v, then derivative of u will be sine ka derivative is cos multiplied by this constant term, this is nothing but this root 3 by 2. Okay, so your ICT becomes, when you multiply this 2 by root 3 inside and take this e raised to minus t by 2 common, then you will get e raised to minus 2 by 2 in bracket. This 2 got cancel and you will be remaining with minus 1 by root 3 sine root 3 by 2 t. Here 2 got cancelled, root 3 got cancelled, then we will be remaining with just cos root 3 by 2t. Okay, so we get our ICT is equals to e raised to minus t by 2. Let us write this positive term first. So it will be cos root 3 by 2t minus 1 by root 3 sine root 3 by 2t. So this is your capacitor current, which is nothing but your resistor current also. Okay, so our VRT will be 1 into IRT. So 1 into multiply by this, it will be same thing. Okay, in question the options were given, that's why I have rearranged all this thing. Okay, in the exam you have to check your option and rearrange all this thing. Okay, so this is our final VRT, which was option B in the question. Okay, in this I have not shown you the option, but in exam the options were given. Okay, So the second sum is from EC 2003. The switch changes its position from 1 to 2 at t equals to 0, and we have to calculate I1 at t equals to 0. Okay, so if you see this is the second type problem. Okay, so this is this type problem where we have to calculate I of 0 plus or V of 0 plus. Okay, so let me tell you, in this we are going to use transient procedure only. Here in first type we have used Laplace transform as we were not having any option, because for higher order sum, basically for the order which is greater than 1, there we can't use transient. Okay, we have to go by Laplace. Okay, here just we have to calculate I of 0 plus. Okay, so till that thing we can use our transient procedure. Okay, so let's see that. So here we have to get our current for t equals to 0 plus. Okay, so first we are going to use our t equals to 0 minus period, and we are going to calculate our Vc 0 minus and IL 0 minus. Okay, so for t equals to 0 minus, this capacitor will be open, this inductor will be short, this capacitor will be open. Okay, so this is our modified circuit. Okay, so from this we have to calculate our Vc1 0 minus, Vc2 0 minus and IL 0 minus. Okay, so here from this you can clearly see that there is no closed path, so IL 0 minus will be 0. And if you observe the circuit carefully, here we have plus terminal connected to this voltage source and this negative terminal is connected to this end. Okay, so you can clearly say that Vc1 0 minus is this V volt. Okay, and if you see this carefully, you will say that Vc2 0 minus will be 0 volt, as this is connected to the negative terminal of the voltage source only. Okay, so here we will have only 0 volt, here we will have V volt, here we will have 0 ampere. Okay, Vc1 is V volt, Vc2 is 0 volt, I1 0 minus is 0 ampere. Okay, now t equals to 0 plus. Okay, in this we will replace this capacitor with the voltage source and the inductor with the current source. Okay, so here we will have this switch to be switched from 1 to 2. Okay, so we won't be having any voltage source present, we will be having this resistor in picture. Okay, so we will having this resistor, then with the voltage source which was Vc 0 minus. Okay, so Vc1 0 minus is V volt, then we have the current source of IL 0 minus which is 0 ampere. Basically this is open circuited. Okay, 0 ampere it means open circuited, 0 volt it means short circuited. Okay, so now here we have Vc2 0 minus which was 0 volt. Okay, so it means it is short circuited. Okay, so if you see this circuit carefully, we have only one current which is flowing from this to this. Okay, and this branch is simply open. Okay, and this branch current is I1 0 plus. Okay, so if we apply KVL, we will get R into I1 0 plus V plus R into I1 0 plus 0 volt equals to 0. Okay, so this V will go to this side, so we will have I1 0 plus equals to minus V upon 2R ampere. Okay, and if you see from the option, you can clearly see this A option is the correct answer. Okay, so this was the type 2 sum, this was the type 1 sum. In type 1 sum we have used Laplace transform, in type 2 sum we have used our same transient procedure. Okay, now let's see this third question where we are given with the condition of our system and we have to get the condition for our RLC. Okay, so in this question, we are given that the condition on RLC such that the step response yt in the figure has no oscillation. Okay, so if you read this question carefully, we are given with the type of system where there is no oscillation. Okay, and we have to get the condition of this RLC. Okay, from the option, and the circuit is here. Okay, so for all this type 3 question, we are going to use our Laplace transform only. Okay, now from the question here you get that your system should not have any oscillation. Okay, and for no oscillation our system must be critically damped or it should be over damped. Okay, this is the control system part. I know that I haven't taught you control system yet, but this is the basic thing that you should know. Okay, so for no oscillation the system can be in critically damped or it can be over damped. Okay, for critically damped zeta should be equals to 1 and for over damped zeta should be greater than 1. Okay, here in this question we want no oscillation, so our condition for zeta will be zeta greater than or equals to 1. Okay, so with this condition only we are going to get all this condition. Okay, so here we are going to use Laplace transform. So first we have to calculate our t equals to 0 minus period. Okay, so from this we will get that Vc 0 minus is 0 volt, IL 0 minus is 0 ampere. Okay, as you can see this ut will be present only from t equals to 0. Okay, it won't be present for 0 minus. Okay, so we won't be having voltage source. It means that whatever the current or voltage will be there in this circuit, it will be 0 volt as well as 0 ampere. Okay, so VC 0 minus is 0 volt, IL 0 minus is 0 ampere. Okay, now for t greater than 0, we are going to use Laplace transform. Okay, so ut Laplace transform will be 1 by s. L ka SL series with the negative voltage source of L into IL 0 minus. IL 0 minus is 0, so it will be short circuited, basically 0 volt. Okay, then R will be same R. Then C will be 1 by CS in series with the positive voltage source of VC0 minus by S. Okay, so here VC0 minus is 0 volts. Okay, so it will be 0 volt only. So we will replace this by short circuit. Okay, so now in the question we have to get our step response. Okay, and using this step response only we have to get this condition. Okay, so here in this circuit you can clearly see that your Yt is present across the capacitor. So basically we have to get the voltage across this capacitor. Okay, so to get the voltage across this capacitor, we are going to use the voltage divider rule. Okay, so we will be having 1 upon SC upon all the resistor. It will be SL plus R plus 1 by SC multiplied by your input voltage, which is 1 by S. Okay, so if you simplify it, it will be 1 by SC. If you multiply this throughout this term, you will get S square LC plus R into SC plus 1 upon SC. This SC got cancelled. So you will be having 1 upon S square LC plus RSC plus 1. Okay, now if you take this input to this side, as we are interested only in the type of the system, so we will be seeing only H of S. Okay, so this is our H of S, so it will be 1 upon S square LC plus RSC plus 1. Okay, now we are going to make the coefficient of S square to be 1. Okay, so for that we are going to take LC common, so we will have S square plus SRC by LC plus 1 upon LC. Okay, so if we simplify it, we will be having 1 upon LC upon S square plus SR by L plus 1 by LC. Okay, so if you see it carefully, we have converted this equation into this second order equation, which was k into omega n square upon S square plus 2 zeta omega n S plus omega n square. Okay, so if you compare this to equation, from this you will get that your omega n square is 1 upon LC. Okay, so from this you will get your omega n is 1 upon under root of LC. Okay, so you got your omega n. Now let's find out this zeta. Okay, so if we compare this 2 zeta omega n with this, we'll get that 2 zeta omega n is equals to R by L. Okay, so from this you will get your zeta equals to 1 by 2 into R by L into 1 upon omega n. Omega n is 1 upon under root LC, so it will be multiplied into numerator. Okay, so here we will be having 1 upon 2 into R into under root of C by L. As you can see that we can write this L as under root of L into under root of L. Okay, so 1 under root L, 1 under root L got cancelled, so we will be remaining with under root of C by L only. Okay, so here we got our zeta as 1 by 2 into R into under root of C by L. Okay, but from the question we know that we want no oscillation. Okay, and the condition for no oscillation is that your zeta must be greater than or equals to 1. Okay, if we take zeta greater than or equals to 1, okay, so it means this part should be greater than or equals to 1. Okay, so if we try to make this into this option form, we want R should be one side. Okay, so we will keep this R to this side. Okay, and we will take all the things to the other side. Okay, so we will be having R should be greater than or equals to 2 under root of L by C. Okay, so the correct answer is R should be greater than equals to 2 under root of L by C, which will be nothing but your option C. Okay, so this is your correct answer. Okay, so in this video we have seen how to deal with all three types of RLC circuit, where first type was where we have to find out the complete IT/VT. Okay, so for that we are going to use Laplace transform. Okay, second type was I0 plus V0 plus. Okay, so for this we have used our transient procedure. The third type was where we have to find out the condition for RLC depending upon the type of the system we have. Okay, so in this also we have used Laplace transform. Okay, so this was all about this RLC based transient sum. Okay, so hope you like this video. So that's it for today. Thank you guys.